Well, with this lecture, I'm going to round off the unit in linear programming, maybe the shortest unit we've had in the course. This also rounds off the entire course. And I just wanted to say something about the question that you're looking at right now, namely, what is linear programming anyway? So we've been using this word, and I never really said what it means. We've given examples of what I've called linear programming problems, but what exactly do we mean? What is a linear programming problem? Well, here's my answer. A linear programming problem is a problem which has two features. First of all, it's a problem in which there is a feasible region determined by linear inequalities. And secondly, the goal in the problem is to maximize or minimize a linear objective function. So if you think about every problem that we've done in this unit, every example, it's always been a case like this. The feasible region was somehow a region determined by linear inequalities, and always the goal was to maximize some simple function, which was linear, as we said. Now, where that feasible region lives depends on the number of variables that you have in the problem. If it's a mixture problem, it's the number of products, but in general, there might be other applications of linear programming. The number of variables that you have determines the dimension in which you're working. One variable means one dimension, two variables, two dimensions, and so on. So if you have one, two, or three variables, then you can think about having pictures that are within the line, which is one-dimensional, or in the plane, which is two-dimensional, or in all of three-dimensional space. And you can interpret the problem geometrically. Now that only gets you a certain distance because in actual applications of linear programming, and there are very many, there might be many more variables. For example, you might be a manufacturer that makes 12 different products, okay? Well, that means that you need 12 variables to set up your linear programming problem to decide what is the best production policy. And that means that in a sense, you need to be working in 12-dimensional space, which sounds perhaps very mysterious and abstract. However, as I've said already, you can make sense of this word corner, and it turns out that there is a corner point principle. So that in fact, you can interpret what you're doing in terms of geometric words and phrases, even though you can't make a picture. Now let's talk about how you solve a linear programming problem. I'm going to tell you a certain algorithm here. And I seem to have left the name out, right? I just put some quotation marks there. You're going to figure that name out. Here is my algorithm. Step 1, list all the corners. Step 2, evaluate your objective function at each corner. Now, if you've thought about those two steps, then you should think the third step's sort of obvious. I've listed all the corners and I've evaluated the objective at each corner. And to maximize, now I just pick out from my list the best corner. So there's what sounds like a very simple and straightforward algorithm. However, there should be something extremely suspicious about this to you. This takes us back to previous material in the course. We've had algorithms like this before, where the first step was to say, list all the possibilities. Remember, for example, we did that in graph theory. And we had a pejorative name for those kind of algorithms. We called them what? Brute force algorithms. That's the missing phrase up there. I was hoping that that phrase would come to your mind. We're talking here about a brute force algorithm. Now, why do we give it this name? Well, first of all, because what it says to do is just use brute force. Just list all the corners, okay? And the problem with an algorithm like that is maybe you really practically can't do that. You see, our examples have been kind of small, baby examples, so we actually could list all the corners. But if you're doing an honest-to-goodness, real-world problem that involves linear programming, maybe it would be impractical to figure out and list all the corners. Maybe there are a million of them. Okay, so maybe that's not the best way to solve the problem. So it turns out that these considerations of how you solve linear programming problems were really driving the invention of the computer in the middle of the 20th century. And one of the algorithms that was developed at about that time was something called the simplex method. So let me describe what the simplex method is, and I will illustrate it by showing you a three-dimensional feasible region. So here is this polyhedron. It has corners and edges and faces. And the simplex method basically works in the following way. Namely, start at some corner. Imagine you're a bug and you locate one of these corners. Now, what you'd like to do is you'd like to decide if you're at the best corner. Well, one thing you can do is you can look along the edges and decide if crawling along those edges will improve your solution. And if it does, well, then you should crawl along that edge. This remind you of algorithms that we used in graph theory, like the nearest neighbor algorithm. So find a direction which improves the solution and follow it and go to the next corner. And now do the same thing. You've come to a new corner. Again, look along all the edges. Now, you don't want to go back the way you came because that will make the solution worse. But there are other edges now available to you, so you can crawl along them. So continue in the same way. You might want to contrast this with what the brute force method says to do. The brute force method says you have to identify all the corners on this solid, and then you have to evaluate the objective function here. Whereas here, this is a much more localized type of solution. You start at one corner, and then you crawl along an edge till you get to a better corner. Now, how do you know when you're finished? Well, you keep crawling and crawling and crawling along edges, visiting various corners, and eventually you'll find yourself at a corner where you can't improve the solution. In other words, crawling along any edge will only make it worse. And as it turns out, because it is a linear programming problem, that's a guarantee that actually you're at the very best corner. There's no better corner available. You're already there at the best corner. So that's how it works. Now, as I've said, the development of this algorithm, which is called the simplex method, really came at the same time as the early history of computing. We're talking about going back to the 1940s. This simplex method was invented by someone named George Dantzig, and it grew up along with computers. Computers were developed in part so as to solve linear programming problems, and this theory of linear programming was developed in part because one could foresee that one was beginning to develop these newfangled gadgets called computers. So this really is taking us back to the meaning of the word computer in its early days. These days, a computer, for most of us, isn't a computer at all. We don't use it to do computations. We use it to post pictures on Facebook and to write messages back and forth and to tweet and so on. And none of that sounds like you're doing computation. But in fact, under the hood, in a sense, there's still lots of computation being done on our computers. And it was much clearer in the early history of the subject that that's what these machines were doing. They were doing computations. Now, this simplex method has worked out very well in practical applications in problems involving hundreds or even thousands of variables, where the brute force algorithm would be ridiculous. Okay, so the simplex method has worked. But even there, it's sort of a limited algorithm in the sense that it might not work out very well because maybe you have to crawl for a very long time. You see, in this simplex method, you're always crawling along the outside of this surface, the outside of this solid. So it's as if you're taking the local train and you might want to go to a very distant station. What might be nicer is if you could just crawl, not just crawl, but actually drill right into the middle of the solid. So it turns out on theoretical grounds there's an even better algorithm. This was developed much later in the 80s by someone named Karmakar, and his algorithm very roughly says don't just stick to vertices and edges, but drill right through the middle. Well, that's really as far as we're going to go. I just wanted to give you some idea that what we had done in the unit on linear programming was just to scratch the surface. It's a much richer and deeper subject, much more complicated and abstract in its applications. But that's really the point we've reached at the end of the unit, and therefore this is the end of everything, the end of the unit, and the end of the course, and I thank you for listening.